Welcome to Bedtime Astronomy. Explore the wonders of the cosmos with our soothing Bedtime Astronomy podcast. Each episode offers a gentle journey through the stars, planets, and beyond, perfect for unwinding after a long day. Let's travel through the mysteries of the universe as you drift off into a peaceful slumber under the night sky.
Imagine for a second, right, that you're just standing in your backyard.
Okay.
And out of absolutely nowhere, from like a completely unknown neighborhood, someone just chucks a snowball right over your fence.
That would be a bit surprising, yeah.
Right. But here's the crazy part. Imagine if you could pick up that snowball and just by analyzing the specific type of ice inside it, you could perfectly map out the exact temperature, the environment, everything about the place where it was made.
Oh, wow. Yeah, that's a wild thought.
It is, and that is exactly what astronomers have just done. But, on a galactic scale, we're talking about a cosmic interloper here.
Right. Comet 3I Atlas.
Exactly. Comet 3I Atlas. And our mission today is to unpack this incredible discovery. We're going to look at how a tiny, almost invisible chemical variation in the frozen water of this comet is literally rewriting our entire understanding of how planetary systems are born.
Yeah, it really is profound. I mean, what's fascinating here is the sheer scale of what this tells us about the universe. We're looking at a cosmic fossil.
A fossil, yeah.
And reading this fossil allows us to basically peer into an ultra-cold alien stellar nursery located somewhere deep, deep in our galaxy.
It's just mind-blowing. Because, you stand on this planet built on a very specific chemical foundation, and you just take it completely for granted every time you turn on a faucet or look out at the ocean.
Right. We just assume the universe plays by our local rules.
We do. But 3I Atlas just fundamentally breaks those rules. But, okay, before we can even dissect the ice and the chemistry, we have to talk about the monumental challenge of actually catching this rogue comet in the act.
Oh, absolutely. The logistics of the observation itself are just incredible.
Because it was actively grazing our sun, right?
Right. The team at the University of Michigan, led by Lucy Salazar-Manzano and Teresa Panica-Carreño, they pulled off something amazing here.
Yeah, because here's the immediate physical problem. If you point a multi-million-dollar optical telescope lens at a blazing star,
you're going to instantly melt your equipment.
Exactly. You just fry it. Traditional optical telescopes are they're designed to gather faint light from ancient galaxies.
Yeah, they're basically giant light buckets.
Right. So pointing that at our sun is like using a giant magnifying glass to burn a leaf, except the leaf is your highly sensitive, irreplaceable sensor array.
Yeah, it's a very fast way to ruin a billion-dollar instrument.
So how do you look at it? I mean, trying to see this comet is like trying to stare at a tiny firefly buzzing directly in front of a stadium spotlight.
That's a great analogy, actually. And the solution was to just abandon optical light entirely.
Oh, really?
Yeah, you can't use visible light. So the team used the Atacama Large Millimeter submillimeter array, which most people just call ALMA.
Right, ALMA.
Specifically, they used its Atacama Compact Array. And ALMA operates in the radio frequency spectrum. So it doesn't even see visible photons the way our eyes or like the Hubble Space Telescope do.
Okay, so it's not taking a picture in the traditional sense.
Not at all. It's detecting long wavelength electromagnetic radiation that gets emitted by cold gas and dust.
That makes me think of like trying to listen to the bass of a car stereo through a solid brick wall.
Oh, yeah, exactly.
Like you can't see the car at all because the wall is blocking your line of sight, which in this case is the blinding glare of the sun. But you can perfectly feel those low-frequency vibrations just bleeding right through the concrete.
That mechanical analogy hits on the exact physics of what ALMA is doing. It's tuning into the radio waves that pass right through all that solar interference. It's like having magical, ultra-polarized sunglasses that filter out the stadium spotlight so you can just see the firefly perfectly.
Wow. That's so cool. And ALMA is down in Chile, right?
Yeah, high up in the Atacama Desert in northern Chile. It's at an elevation of over 16,000 feet.
Wait, why does it need to be so high up?
Because water vapor in Earth's own atmosphere actually absorbs submillimeter radio waves.
Oh, I see.
Yeah, so if you build ALMA at sea level, Earth's humidity acts like a heavy blanket. It just muscles that base, keeping with your analogy, before it ever reaches the dish.
So they put it in a bone-dry desert, super high up.
Exactly. Up there, the array has a crystal clear, unobstructed view of those radio frequencies.
And they really needed every ounce of that clarity, didn't they? Because The window for this was terrifyingly tight.
Oh, incredibly tight.
They caught 3 Iacles just 6 days after its perihelion, which is the point where it physically flew closest to the sun.
Right, the absolute closest approach.
But, okay, let me push back on that for a second. Why wait?
What do you mean?
Like, why wait 6 days? Why not point ALMA at the comet months earlier when it was further out in the solar system, moving a bit slower, easier to track?
Ah, right. Because when a comet is deep in space, it is chemically silent.
Chemically silent.
Yeah, it's just a dormant, frozen rock. The molecules inside it are completely locked into a solid crystalline matrix. If you want to read its chemistry, you actually need those molecules to become an active gas.
Oh, okay, so you need the sun to bake it.
Precisely. As the comet approaches the sun, it crosses what we call the snow line. The intense solar radiation starts to bake the surface, and that causes the ice to sublimate.
Sublimate, so it skips the liquid phase entirely.
Right. It goes straight from a solid into a massive expanding cloud of gas, which astronomers call the coma.
So the sun is basically acting as our laboratory furnace.
Exactly.
But wait, that still doesn't fully explain the 6-day delay.
No.
Well, if perihelion is the moment of maximum heat, wouldn't that be the exact moment of maximum gas release? Why 6 days later?
That comes down to a really interesting concept called thermal inertia.
Thermal inertia, okay.
See, the outer layer of a comet is rarely pristine white ice. It's usually this very dark, porous crust made of carbon-rich dust and organic compounds.
So it looks more like a charcoal briquette than a snowball.
Exactly like a charcoal briquette. So when the sun hits that dark crust right at perihelion, the surface heats up instantly, but it takes time for that thermal wave to physically penetrate down into the deep interior of the nucleus.
Oh, where the ancient pristine ices are actually buried.
Right.
So the 6 days post-perihelion is the thermal lag.
You got it.
It's the time required for the sun's heat to, like, bore through the protective outer shell, crack open the vault, and trigger those deep-seated ices to violently expand and shoot out into space.
And that violently expanding gas is what ALMA is actually listening to.
Man, the timing on that. If they missed that window, the whole thing would just cool down and vanish back into the void.
Yeah, it would have taken its secrets with it forever.
So, okay, they successfully recorded this chemical signature out of the sun's blinding glare. But what exactly is boiling off the surface? Like, why do astronomers call it a cosmic fossil?
Well, we have to understand what a comet physically is. They are famously nicknamed dirty snowballs, as we said.
Right.
They're incredibly rich in water content, mixed with all that dust and primordial rock. And because they spend billions of years in the deep, near absolute zero freeze of interstellar space, their internal chemistry just doesn't change.
Doesn't degrade at all.
Nope. It doesn't degrade, it doesn't interact. The water inside is literally frozen information. It's a perfect time capsule from the exact moment and location the comet first coalesced out of a stellar nebula.
So they aren't just hazards or pretty streaks in the sky. They are literally the universe's flash drives.
That's a perfect way to put it. They're randomly delivering data about alien star systems directly to our doorstep, so we don't have to travel light years to study them.
It's like, think about ice core samples taken from Antarctica.
Right, paleoclimatology.
Yeah, scientists drill down and they get these ancient air bubbles trapped in the ice, and that tells us about Earth's past climate. Comets are doing the exact same thing, but for the whole galaxy.
Exactly. Panecka Carreño notes that each interstellar comet brings a little bit of its history, its fossils, from elsewhere.
So what does this all mean? If it's just frozen water, isn't water the same everywhere in the universe? I mean, H2O is just H2O, right?
Yeah.
A glass of water here is a glass of water 1,000 light years away.
And that assumption is exactly what this discovery shatters.
Yeah.
Yeah. Water is not a monolith. While comets and our oceans do contain standard H2O, they also contain a variation, a rare anomaly called semi-heavy water.
Semi-heavy water. Okay, what makes it heavy?
It's deuterated water, or HDO.
HDO.
Right. Normal hydrogen is just one proton, one electron. Super simple.
The most abundant element in the universe.
Exactly. But deuterium is a heavier isotope of hydrogen. It has that same proton and electron, but it also has a neutron sitting in the nucleus.
Okay, an extra neutron. That doesn't sound like a huge deal.
Well, it literally doubles the mass of the atom.
Oh, wow, yeah, a 100% increase in mass for a single atom is massive.
Exactly. So when that heavy deuterium bonds with an oxygen and a normal hydrogen, you get semi-heavy water, HDO. And because of that extra mass, it behaves totally differently on a physical level.
Like how?
It freezes at a slightly higher temperature. It's noticeably denser. If you drop an ice cube made of heavy water into a glass of regular water, it'll actually sink to the bottom instead of floating.
Wait, really? It sinks?
Yeah. And it has huge effects on biology, too. If you were to drink heavily concentrated deuterated water, it would eventually be fatal.
Fatal from water?
Yeah, because the heavier mass of the deuterium atom forms stronger, more rigid hydrogen bonds. It physically jams up the fast-moving protein machinery in our cell.
Oh, man, so it just breaks our biology.
Pretty much. It famously prevents kinetochore microtubules from pulling chromosomes apart during cell division. So cell division just stops.
That is wild. It's a completely different chemical reality, even though it's technically still water.
Right. But for astronomers, the real value of HDO isn't its toxicity, it's the fact that it acts like a cosmic barcode.
A barcode?
Yeah, because we have a very specific baseline for this barcode in our own local solar system. On Earth and in comets native to our system, there is roughly only 1 molecule of semi-heavy water for every 10,000 molecules of ordinary water.
1 in 10,000, so it's super rare.
Incredibly rare. It's a very faint signal.
It's like finding a microscopic typo or a misprinted coin.
Yeah, exactly.
Like, if you have a giant bank vault with 10,000 regular pennies, finding the one penny stamped with a slightly different date tells you exactly which rare mint it came from.
That's a great way to visualize it. And finding that 1 in 10,000 molecule on a rock speeding away from the sun at over 100,000 miles per hour, that's why LMA was so critical.
It's an astronomical needle in a haystack.
It really is. But if we connect this to the bigger picture, the true shock wasn't just finding it.
No,
it was finding the baseline that it's measured against and where that deuterium comes from in the first place.
Okay, so where does it come from? How does this extra neutron get in there?
We actually have to trace the timeline all the way back to the first few minutes after the Big Bang.
Oh, wow. We're going all the way back.
We have to. This period is known as primordial nucleosynthesis. The universe was hot and dense enough for protons and neutrons to fuse together. This is when all the hydrogen and helium in the universe was forged.
Right.
And deuterium was created during this very chaotic window.
But the universe was expanding rapidly, right? It was cooling down.
Yeah. Crucially, yes. It expanded and cooled so fast that the nuclear fusion process was abruptly halted.
Halted.
Yeah. If the universe had stayed hot and dense for just a little bit longer, all of that deuterium would have fused into helium, and there would be no heavy water anywhere in the cosmos.
Wow.
But the rapid expansion froze the process in place. It left a fixed, universal ratio of deuterium to regular hydrogen scattered all across the cosmos.
Okay, so the raw materials for a stellar nursery are identical everywhere.
Basically, yes.
Like a giant molecular cloud of gas condensing to form a star in the Andromeda galaxy has the exact same baseline ratio of hydrogen to deuterium as the cloud that formed our own solar system.
Exactly. The universe provides the identical starting ingredients, but the local environment is what drastically changes how those ingredients combine into water.
Here's where it gets really interesting. Wait, if the Big Bang set the ratio everywhere, how does a local environment change it?
The primary driver of that change is extreme cold. The team highlighted that the chemical pathways required to actively concentrate deuterium into forming water ice, they require ambient temperatures dropping below roughly 30 Kelvin.
30 Kelvin. That translates to about minus 406 degrees Fahrenheit.
It's staggeringly cold.
Yeah.
Vastly colder than anywhere on Earth, colder than the dark side of our moon. It's hovering dangerously close to absolute zero, where atomic motion itself almost stops.
So how does that cold environment physically act as a trap? The researchers use the phrase thermodynamic sieve, but what is the actual mechanism making the heavier water win the race to form ice?
It revolves around a quantum mechanical principle known as zero-point energy.
Zero-point energy. Okay, break that down for me.
Even at absolute zero, molecules retain a baseline level of vibrational energy. Because deuterium is twice as heavy as normal hydrogen, the chemical bond it forms with oxygen has a lower zero-point energy.
So it sits deeper in the potential energy web.
Exactly, meaning it is physically harder to break an oxygen-deuterium bond than an oxygen-hydrogen bond.
I see.
So picture the vast swirling molecular clouds of a stellar nursery. You have all these microscopic dust grains floating around.
Right, the dirty part of the dirty snowball.
Yes. And these grains act as tiny catalytic surfaces. Oxygen atoms land on a dust grain, and hydrogen and deuterium atoms are just bouncing around on the gas, constantly attaching to the oxygen, and then getting knocked back off by ambient thermal energy.
Like musical chairs.
Kind of, yeah. But when the temperature of the entire cloud drops to 30 Kelvin, there simply isn't enough ambient thermal heat left to knock the heavier deuterium out of the bond.
Because it's sitting deeper in that energy well.
Precisely. The lighter hydrogen atoms have a shallower energy well, so even that tiny amount of 30 Kelvin heat is enough to agitate them and break their bond. They just bounce off.
But when a deuterium atom locks in, it is secured. The cold just starves the system of the energy needed to reverse the reaction.
Yes. As the ice mantle builds up around that dust grain layer by layer, it selectively hoovers up the heavy deuterium, permanently locking it into the frozen matrix.
Man, that is fascinating. So the atoms exist everywhere, but the cold acts like a sorting mechanism.
Right. And because comets are uncontaminated time capsules, as we discussed, the moment that ice forms, the ratio is locked in forever. The HDO to H2O ratio becomes this pure, uncorrupted thermometer.
That's brilliant, because you can't rely on complex molecules.
Exactly. Complex molecules like methanol or simple sugars, they can form through a variety of radiation exposures and energetic shocks over billions of years. Their presence is ambiguous.
But the deuterium ratio is tied directly to quantum bond strengths and raw thermodynamics. It tells you exactly how cold the oven was when the comet was baked.
Beautifully said.
So we know the universe set the raw baseline. We know the quantum mechanics of how ultra-cold temperatures trap the heavy isotopes.
Yeah.
And we know our own solar system produced a 1 in 10,000 ratio.
Right.
Which brings us to the data ALMA pulled from 3I Atlas. What was the ratio?
This is the climax of Salazar-Manzano's analysis. The revelation is that the HDO to H2O ratio in 3I Atlas is more than 30 times higher than the comets formed in our solar system.
30 times higher.
Yeah, and more than 40 times the ratio found in Earth's oceans.
That is just. A 30x multiplier is not a rounding error. That is a completely different regime of physics.
It totally is.
Because if the zero-point energy trap requires profound cold to concentrate deuterium, then a 30x spike means 3I Atlas didn't just form in a cold environment.
No, it formed in an absolute deep freeze, far colder than anything present during the birth of our own sun and planets.
It implies a fundamentally different structural evolution for its home system, doesn't it?
Oh, definitely. Our solar system formed relatively close to massive hot O-type stars. They flooded our local stellar nursery with ultraviolet radiation and ambient heat,
which kept our local dust grains warm enough to prevent massive deuterium enrichment. So we got the standard 1 in 10,000 ratio.
Right. But 3I Atlas must have formed in a dark, isolated, profoundly refrigerated pocket of a giant molecular cloud.
Just sitting in the dark.
Yeah. The gas and dust coalescing into its parent star were subjected to minus 406 degrees Fahrenheit for an incredibly long time. That allowed the ice grains to aggressively stockpile heavy water before the star ignited and blew all the remaining gas away.
Salazar-Manzano's conclusion is unequivocal then. The cloud of gas that formed this comet's home system had utterly different thermodynamic conditions than the environment that created our solar system.
Completely different. And yet, despite being born in a distant, isolated deep freeze, it somehow ended up flying right through our sun's corona.
Which is crazy, because the violence required to make that happen is staggering. We're looking at a rock born in a quiet, freezing nursery, which means it had to be violently ejected from its home star's gravitational grip to become an interstellar wanderer.
Right. The mechanics of interstellar ejection usually involve catastrophic multi-body interactions. Well, as a new star system forms, giant gas planets, similar to our Jupiter or Saturn, condense out of the protoplanetary disk. But their orbits are rarely stable initially. They interact gravitationally with the massive disk of remaining gas and dust, and that causes them to migrate.
Oh, like the Grand Tack model in our own solar system.
Exactly. Where we think Jupiter migrated inward toward the sun and then pulled back out, scattering millions of asteroids and comets in the process.
So in the system that birthed 3I Atlas, a similar, perhaps even more violent migration must have taken place.
Most likely. A migrating gas giant, or perhaps the gravitational perturbation of a closely passing neighboring star, acted like a cosmic slingshot.
Wow.
It transferred immense orbital momentum to this specific comet, accelerating it completely beyond the escape velocity of its parent star.
Throwing it out into the galactic wilderness at hundreds of thousands of miles per hour.
Yep. And it just wandered through the dark, empty expanse of the Milky Way for millions, maybe billions of years, in total silence.
Until By pure, blind, cosmic chance, its trajectory threaded the needle of our inner solar system.
Exactly. It dived toward our sun, sublimated its ancient heavy water ice, and right at that exact moment, the Alame Array in the Chilean desert was listening.
The serendipity of that event is just. It's matched only by the scale of what it teaches us.
It's true. Astronomy has long operated on the assumption of mediocrity.
The idea that our solar system is a standard, run-of-the-mill template for the rest of the galaxy.
Right. We naturally project our local chemistry onto the stars we see in the night sky.
But 3I is the physical proof that planetary evolution is wildly diverse. The recipe that created Earth, with its specific isotopic balance, is literally just one flavor out of an unimaginable spectrum.
Yeah. The galaxy is actively manufacturing planetary systems under conditions so extreme that they break our local chemical baselines by a factor of 30.
It forces a massive revaluation in the field of astrobiology, doesn't it?
A huge one. We spend so much time looking for exoplanets in the Goldilocks zone.
Right, the orbital distance where temperatures allow liquid water to exist on the surface.
But we always assume that the liquid water behaves like Earth's water.
Oh, wow. Yeah. What happens if you have a planet in the Goldilocks zone of an alien star, but its oceans are formed from the heavily deuterated 30x concentrated ice of 3I?
That's the million-dollar question. An ocean of heavy water is denser, it's more viscous, it absorbs different wavelengths of light, altering the thermal dynamics of the planet's climate.
And more importantly, as we discussed earlier, it poses a severe evolutionary hurdle. Heavy water actively disrupts terrestrial cellular mitosis. The strong hydrogen bonds of deuterium jam the mechanical pathways of DNA replication.
Exactly. Which means if biological life were to spark in a highly deuterated ocean, the fundamental architecture of its cellular machinery would have to evolve completely differently than life on Earth.
It would have to. Its proteins, its cellular division mechanisms, its entire biochemistry would need to be engineered to handle the massive kinetic isotope effect of an environment steeped in heavy hydrogen.
We aren't just talking about different environments here. We are talking about the potential for a completely unrecognized parallel track of biology.
That is just wow. And that is the ultimate legacy of 3I, isn't it?
I think so, yeah.
It was a fleeting visitor, visible for just a matter of days before retreating back into the interstellar void. But by leveraging the unique capabilities of radio interferometry, astronomers were able to decode the frozen thermal record it carried.
It really reminds us that every time we think we have the universe figured out, it throws a snowball over the fence that rewrites the rules.
It really does. We are built from a very specific 1 in 10,000 recipe. But somewhere out there in the ultra-cold, heavily deuterated deep freezes of the Milky Way, the galaxy is cooking with an entirely different set of ingredients.
And we now have the physical proof that those strange alien nurseries are actively seeding the cosmos.
It just makes you wonder, looking up at the night sky tonight, what strange, completely unrecognized forms of chemistry and perhaps entirely different forms of life might be brewing out there in the dark.